Okay, we'll finish this introduction to functions with what's known as the inversion theorem. So this is a theorem that tells us when a function has an inverse. So here's the statement. Let f be a function from x to y. All right, then f has an inverse if and only if it's bijective. All right, this is an if and only if statement, so there's two conditional statements to prove. That's why this video is in two parts. We'll do one part in each video. So let's start our proof here. Part 1 is going to be the forward direction, meaning we're going to assume f has an inverse, then show it has to be bijective. So let's suppose f has an inverse, and I will call it g. So g is this function from y to x that's inverse to f. So we need to use this to show that f has to be bijective. Remember, if f and g are inverses, then when we compose them, we always get an identity function. Depending on the order in which we compose them, it's an identity on y or an identity on x. Now, we want to show that f is both injective and surjective. That's what it means to be bijective. So I'm going to start with the injectivity part. Let's say that a and a prime are elements of x such that f of a equals f of a prime. So this is how we start an injectivity proof, and our ultimate goal is to show that a and a prime actually have to be equal. So what I want to do now is actually take these values, f of a and f of a prime, and plug into g, because we know something about the composition of g and f. So we're going to use that to our advantage. So we know g of f of a has to be equal to g of f of a prime. All right, f of a and f of a prime are the same number, the same value, so when we plug that into g, it should produce the same result. But what do we know about g of f of a, right? Since f and g are inverses, we know that g composed with f is equal to the identity function on x. What does the identity function do? It takes in an input and it just spits that back out as output. So that means that g of f of a is really equal to a, and g of f of a prime is really equal to a prime. So we actually do have the thing that we want. We have a is g of f of a. We said g of f of a is equal to g of f of a prime, and that we know is equal to a prime. So a and a prime really are equal, and f is injective. All right, so that's half of the bijectivity proof. We now need to prove f is surjective. So how do we do that? We need to show that the image is equal to the codomain. So I'm just going to pick anything in the codomain y and show that it's in the image of f. So now let b be inside y. I need to find some element in x such that f sends it to b. Okay, and that'll show that our function f is surjective or onto. So if b is in y, that means that g of b is contained in x, right? G is this function going from y to x. Okay, so we can find this element here in x, and now again we use the fact that f and g are inverses. That's really all we have to go on, right? We're using the fact that f has an inverse to show that it has to be bijective. So since f and g are inverses, Now we're composing in the opposite order. We have the following: f composed with g is equal to the identity function on y. So when you plug in elements from y, it just spits the same elements back out. All right, so what does this mean? This means that f of g of b is equal to b. So if you take any element b inside y, we can always find an element in x that gets mapped to it by f. And that means that f is surjective. So therefore, f is surjective, and it is bijective. Okay, so again, in this part of the proof, we're just assuming f has an inverse, so we know what it means for a function to have an inverse, and we're using that to show it's both injective and surjective, which makes the function bijective. All right, part 2 coming up.